All right. All right, let's start. So today we're going to be looking at a univariate polynomial commitment scheme, right? Called FRI. Um, this is the cryptography that is used in this is hashing, right? So as long as you have a hash function, that's basically the only cryptographic assumption that is being made here. So KZG had the discrete log assumption, for example, based on like elliptic curves and everything. So this one, the only assumption is just that you have a hash function. Okay. Um, this is it uses a lot of components. So we'll go over them bit by bit. I guess the first one we'll work on is like Meko trees. Okay. So you use Meko trees to kind of like commit. So I don't know. I think Francis talked about using Meko trees as a commitment scheme, right? Yeah. So Merkle trees are used as a vector. You can use it as a vector commitment scheme, right? So you have a vector. A vector is, you can also think of it as like an array, right? So you have an array of field elements. Okay. So you want to commit. What's the goal of commitment? The goal of commitment is that you want to be able to like be bounded by some message or some vector or some polynomial. That's why I'll ask you in the future to give me the evaluation of this vector or this polynomial at a certain point, and I want to be sure that you're not just giving me one random evaluation, right? You are giving me the evaluation from the vector or the polynomial that you have committed to, right? I want to hold you to this commitment. So that's why you need to commit first before I ask you to open. Because if I ask you to open before you commit, then you can change it to anything you want to change it to. The most favorable one for yourself. So you ask for commitment first so that the person is like tied to this, and then you cannot ask for whatever it is that you want to ask for. So Merkle trees are not polynomial commitment schemes, but they are vector commitment schemes. Polynomials are different. They have this notion of a degree, but vectors don't have that. So FRI is using Merkle trees plus something called a degree test, a low degree test. So it's combining those two things in order to create a polynomial commitment scheme. A low degree test. Low degree test. We'll still get into all of this in more detail. So a low degree test to kind of like. So let's start with just like Merkle commitments for vectors, right? So let's say you had 8 elements, okay? You had A, B, C, D, E, F, G, H. This is your vector. You want to commit to this vector. How do you do this? You take 2, you pair them up, right? And then you hash those 2. So this is going to be the hash of. So I'll just call it like A. Cool? Yeah. Right? Make sense? Then you take this 2 also. Cool? And then you finalize. I'll just call this one Makes sense? So this here is called the root hash. Also your commitment. Now this commitment is what you're going to send over to whoever asks you to commit to this. Now this has kind of like forced you, so any future queries I make, it binds you to this vector. So you cannot just change anything in this vector without it changing the commitment. And because of that, if you try to deceive me, I would know. Because whatever proof you give me would not match the hash that the commitment that you already gave me. Makes sense? So now let's see how to generate a proof. Let us say I asked you to open index let's say I asked you to open index 2. That's C. Yeah. Yeah. It is a lot of it is Meku trees. But we're not talking about FRI now. We're just talking about Meku trees in general. So how vectors and polynomials are different? So polynomials have the concept of a degree, right? You can represent a polynomial in evaluation form, which is also the same thing as like having a vector, right? But then that vector is supposed to have an associated degree with it. So let's say this was a degree 2 polynomial, right? So if you have a degree, let's say you had a straight line. A straight line only needs 2 points, right? So let's say I had f of x is equal to 2x plus 1. I can evaluate this at 0, which will be what? And I can evaluate it at 1, which will be what? 3, sorry. Right? But then I could also evaluate it at like 10 more points. Correct? So I can evaluate it at 2, which will be, I can evaluate it at 3. I'm just trusting you. I can evaluate it at 4. Okay. So this vector here represents a degree what? A degree 1 polynomial. Yeah.
Is it vector as a vector?
It's the same thing. Yeah, just like it's holding a list of array, anyone you want. But more like it's just holding a list of values for now. But then I guess you could still, when we get into like code words and everything, we'll see more. So like if you take all of this, the 5 values, and you interpolate it, you're going to get 2x plus 1, right? Which is a degree 1 polynomial. Okay? But the problem with just like using a Meku tree to commit to this is that Meku tree does not keep track of the degree. So I could have also gotten like 5 random values here, right? I could have done like 8, 3, 4, 9, 12, right? If I interpolate this, more likely than not, I'm going to get a degree 4 polynomial. You know, d plus 1 point, right? So more likely than not, I'm going to get a degree 4. But Meku trees would not. So you probably could say, okay, yes, I'm committing to a degree 1 polynomial. But then it just chooses 5 random points and commits to that. There's no way for you to know whether that commitment was actually a degree 1 polynomial, which the protocol said it should be. You get? So that's the difference between like just vectors and polynomials. Polynomials have like the data, but then they also have this associated degree. And in most protocols, you want polynomials of a certain degree, right? So you need a way to somehow like verify that this thing that this guy has committed to is of this degree. That is where powers of tau in KZG comes in. So like the powers of tau is putting a maximum degree bound. So let's say you had powers of tau is like tau to the, I guess, 1, no, 0, 1, right? Up to some number, let's say tau to the 4, right? Nobody knows tau, right? So if the powers of tau stops at tau to the 4, then it is impossible for you to commit to anything greater than 4. That's like degree 4. You get? So that's placed like a limit on the degree. So now I don't need to see what you have done. I just know that because you are using the tau that I've given you, you cannot pass this degree. And the protocol is always like, this person should not be able to pass this degree. It's putting a limit on the degree. So you want a way to figure out whether the committed thing is below a certain degree bound. It's not just enough to commit. You need to also make sure that it is below a certain degree bound. So powers of tau achieves that in KZG. So KZG is doing two things. It's committing to the values, but it's also ensuring that the values are below a certain degree bound. Merkle trees allow you to do the committing, but they don't allow you to do the degree bound placement. So FRI basically figured out how to do the degree bound placement. And that's basically what we're going to be talking about today. Like, how do we do this degree bound placement? Cool? Degree bound. That's like, it just like checks that this thing is below a certain degree. So let's say like your protocol only wants to work with less than or equal to degree 20, right? So you need to make sure that it is actually not more than degree 20. So you didn't commit to a degree 22 or a degree 25 or a degree 30 polynomial. Okay? So FRI is like a way to ensure that this is the case. So now, Merkle proofs. Does the commitment make sense?
Yes.
Cool? Now I want to figure out how to generate a proof. So I want to open index 2. So what you kind of do is that you generate like a partial tree. Something that allows you to get back to where you came from. And the way you do that is that you get siblings. So this is what we are trying to prove, right? So we give the sibling of that. Okay? We give the sibling. So the sibling is like, everybody is like always pairing. Right? You're always pairing to get a new one on the top. So your sibling is your second. Yes, the other pair. Okay, so this is what we're trying to prove. So we just get its sibling. So let's say this is our proof. Our proof is basically going to be equal to D, sorry. D at first, which is the sibling. Now we have C and we have D, which automatically means we have CD, right? We have all information needed to create that CD. So that means that's redundant information. We don't need to send CD. But then we don't have the sibling of CD. So we also send the sibling of CD. So that will be, okay? Remember we have CD by proxy, right? And now we have AB concretely. So that means we have this. So that means we need to only send with this, we are done. And that's the proof. Essentially, that's the Merkle proof. Does this make sense? Should we go over a different example? The same one? Okay. So, we're trying to prove C, right? We're trying to... Yes, we are trying to prove that C is a part of the tree, right? So, you you want to basically give enough information to reconstruct the root hash. That's the goal. You want to give enough information to reconstruct the root hash. But then you don't want to give more than you need to give. Okay? So C came together with D to give you CD. There's no way you can figure out what CD is because you're trying to go up. You're trying to go up. You need to get this hash, you need to get this hash, and finally you need to get this hash. So to get this hash, you are missing info. Right? You cannot just know that CD from just C. Right? So you need the D. You need this, right? So that'll be the first element in your proof. Now that you have these two, you can compute CD. Cool? Now for CD, you need to get the parent also, because you're trying to move up. So you need A, B, C, D, but you only have CD. So that means that you need the sibling also, which is AB. So that's why the next element in the proof is AB. Now that you have AB and CD, you can get this one by proxy, right? So now you need to go up again, but you cannot just go up. You need the sibling also. So that's why the last element in the proof is that sibling, and then that's the final thing. Does it make sense?
If we want to multiply some names, which is D, you want us to give us the same thing.
No. So the first element will now be C,
Okay.
but then the rest of them are the same. Yes. Cool.
So must it always come from the
Leaf.
layer? The
Yes.
leaf? Okay.
Yes. You're always showing membership of the leaf. Yes. It's a part of the tree.
So, going to do that, so I need to balance the numbers that are assigned here or specifically index like 0 or 1.
It's just based on these numbers. I was just trying to specify that you see that I'm trying to open. Make sense? Does proof generation make sense?
Yes. Yeah.
Okay. So now that we have the proof generation, there's now the verification step. So how do we verify this? So when you ask to show that C is a member, the thing that the prover returned was that C is indeed a member with the following proof, right? This proof is called the Merkle authentication part. It's called the Merkle authentication part. It's like a way to authenticate the statement that C is a part of the list. Okay? So now to verify this, it's very simple. All we do is we just do repeated hashing. So we hash C with the first element of the proof, which is D in this case, right? So it's like we hash C, D to give us what? Then we take this new thing and use it to hash with the next one, right? So like we hash. There's something about the index, but we'll skip it for now. So that'll give us what? Then we take that and we use it to hash the last one. It's different, yeah, it's different. So that's what I was talking about. Like the index is different. But let's continue first. Does it make sense? Cool? Not cool. Okay. So the goal is that we want to get back the root hash at the end of the day. That's how we will know that everything was done correctly. And the root hash is A all the way to H, right? So what we do is that we take the thing that we're trying to prove, right, which is C, and then we take the first element in the proof, then we hash the two of them together. So we're going to get a new item here, which is CD. The hope is that that's the first parent. Okay? And to get the next parent, we take this new thing that we got, and then we hash it with the next thing in the proof. And then we're going to get a new parent again, which is this one that is on here. It's basically just following the same way you generated the proof, in the sense that you knew that you wanted to get this, but to be able to get this, we knew you wanted to get this, but to be able to get this, we had to give this, right? So that's like what's the first element of your proof. So you're just doing the reverse. You're now saying that, okay, the prover has already helped me with all the information I need to get the parent. So let me just take that, and then I just hash the two of them to get CID. Then now that you have this, you know that you want to get this. But then you already know that the prover has given you this. The prover foresaw that challenge, and it gave you the required information for you to get past that obstacle. So you take the next thing, and then you hash it together to get ABCD. So now you have this, and you want to get this. The prover foresaw it also, and provided you with this. So you now take these two, and then you can get the original listing back. Does it make sense?
What are we talking about?
Yes. So the problem with this, as I've described it, is not enough for implementation because of the order in which you hash things would change the results, right? You cannot just hash. If you hash A and B, you're going to get what? A, B, right? And if you hash BA, you're going to get these two are not equal. They are not. All of them are. Look, depends, yeah. But all the ones we are using are not. Right? So the order matters. So this means that in your algorithm, you need to somehow know whether this term is like an even term or an odd term. So you can see that this is an even position. So the even position always comes first, then the odd one. So if you see that it's odd, you just take the other guy and put it at the front. But if you see that it's even, you put it at the back.
So how do you now do the case of zero?
You said? It's based on the index. You said something? Israel, what did you say?
How do you take care of zero?
Like if you're trying to prove zero.
Is zero even?
I'm not entering this journey with you, bro. Yeah. It depends on. It all depends on your structure, right? But yeah, you can see that the way we hashed it is like we put A then B, right? So if you have two siblings here, you should, based on the index, know where to put what. Makes sense. But this is not like, there's still more details when it comes to implementation, but this is like sufficient to understand like Merkle proving. Make sense?
Yeah.
Commit, prove, verify. Sure?
Yes.
Sorry, my question is,
Yeah.
what is back again? The whole point of having that proof, this method education part,
Yeah. Is to prove that C, for in this case, is in the vector. You know, you committed to a vector. And then, let's say I asked you, is C in that vector? And you say yes. Then I cannot just take your word for it. Prove to me that it is. Without sending me, let's say, like the full vector. So that proof is like a way to show that it is, by only sending some intermediate values. So it's very small relative to, you only need to send log n values. So like the proof size is log base 2 of the number of leaves. So if you have 8 leaves, that will be log base 2. And that's why we have just 3 elements here. Okay? So if you know the amount of leaves you have, you can figure out how big the proof is going to be.
So there's something Frank said that for cases the proof size
Proof size is constant for KCV. Commitment size is constant for and proof size is constant.
yeah, that was it.
Yeah.
So for this one now,
It's not constant
it's not constant
at all.
So that means
That's the proof size.
Everything. Commitment is not constant. No, it's not
But
constant.
this should be constant because is it not a field? It's not a hash.
For this one,
Yeah, for Meku, I talk about Meku now, not
Yes.
FRI.
No, Meku.
And yeah, constant.
for FRI,
It's not constant.
So both complement and proof in FRI are not constant.
I don't know how it became.
So this is another thing you need to understand. Like group operations are expensive relative to field operations. So that's like doing 10 multiplications or 50 multiplications might cost the same as doing one group exponentiation. So it's not just about the size, it's also about the amount of work needed to perform that elliptic curve. You know, you draw the line and then you trace it down. That's costly.
That's what?
Costly. Like it's expensive to do that. So most of the old proof systems, linear parameters is like expensive again, but the proof size is really short. That's like the key thing. So people that do on-chain verifiers that are sending the proof to a smart contract where gas is so expensive, you can see why they are deviating towards KZG style proof systems. Because of the amount of data you need to send over there is like really small. So most people, there's something called recursion, where you take, let's say, a stack proof, or let's say a GKR proof, and then you wrap it in a GROT16 proof, which is its KZG. So it's like it's really small. A GROT16. I'll write it, don't worry.
When you use your app,
You can wrap it, yeah.
what does that do?
It reduces it I guess do the best of both worlds. So sometimes like these proof systems that are based on KCG and they are slow in terms of like the prover time. The provers are usually slow, but the proofs are usually small. Okay? Prover is slow, proof is short. The new generation protocols, prover is fast, proofs are large. Okay? So we have some that have like fast provers, large proofs. Then slow provers, small proof.
I think for Stapley use the first one, the fast mover,
Large. Yes. But then they have a GROT16 recursive verifier. So the recursion is now a way to get the best of both worlds, where you can now have a fast prover and a small proof. Right now you can't have it in the same protocol, but you compose protocols together to now have it. So this is what is happening. This large proof, right? It has a verifier. Cool. What you do is that you now implement the verifier in the other proof system. So you prove that you verified it correctly. I don't know if that's making sense. So you have a statement, right? This is the statement you want to prove. This is the statement you want to prove. you wrote this statement in the first paradigm. Okay? So anything you want to prove, you have to write a circuit for it, right? So let's say you write the circuit in. Let me just use GKR for this one, and let me use grad 16 for this one. Okay? So this is the computation that you want to prove. You write this statement in a GKR circuit. Okay? Now this statement can be like really, really big. That's why you even want a fast prover, because the statement is really huge. So when you do this, your GKR prover would now prove this GKR circuit, right? And output what? A GKR proof. Okay? Normally, you will not pass this on to your verifier, which is written in regular Rust. And then your verifier will verify and return a bool that it was valid or it was invalid, right? But now, that verifier is not just regular Rust anymore. You now write a GKR verifier, which is just another statement. Like circuits are a way to encode any computation. So verification of a GKR circuit is also just a computation. Okay? So you're going to write the GKR verifier in so you write the GKR verifier in a grad 16 circuit. So it's still capable of verifying the GKR proof, but it can also prove that it verified it correctly. Does that make sense? So when it's verifying it, it's also proving that it's doing this verification correctly. Then it too will not come up with its own grad 16 proof. So as this one is verifying, as it's verifying it, it's going to now output that's way shorter. That's way shorter. But then, you know, the goal of ZK in general, right, is that the proof should be much smaller than the statement. Right? So, if you're, let's say you're using a grad 16, okay, let's give some concrete numbers. Let's say the statement originally was 1,000 lines. Let's say 1,000 lines of, I don't know, just 1,000. That's the unit for the statement. When you have done the GKR proof, the proof should be much smaller than the statement. So let's say this GKR proof now is like 5 lines. Okay? Now you're writing a grad 16 prover, which is slower. Okay, let's say a GKR prover is let's say a GKR prover takes let's say a grad 16. Let's say a GKR prover adds a 2x overhead. Okay? We are proving something with GKR. It adds a 2x overhead. Okay? So this 1,000, the statement was 1,000 units. When we prove it with GKR, the cost in terms of time will be like 2k, right? Like 2x overhead. Make sense? Mm-hmm. And let's say the GKR, the grad 16 prover adds a 10x overhead. Okay? So if we had proved this initially with grad 16, we would have 10,000 compared to 2,000. But now, instead we used GKR to prove it, giving us a cost of 2k. Then we now used grad 16 to verify that proof, which was 5 lines, right? Giving us that the grad 16 cost is what? 5 times 10. Can you see? Which is 50. So total cost in terms of proving time is just... Does it make sense? Like you took a really big statement and then you used a fast prover to generate a proof. But then that proof is much smaller than the original statement. So you can now use a slow prover to prove this smaller statement and prove the verification of this smaller statement. Does that make sense? Which will lead to like less overhead overall. Because if you had just used gross 16 straight away, you will have had 10K, which is like much bigger than this. But then if you had only used GKR, which is like smaller proving time, technically, right? Because it'll be like 2K, but now it's 2K50, but you will have bigger proofs. But combining them, you get the best of both worlds. That like, your prover is not as fast as GKR normally, that's fine, but it's close to it. But then your proof is no longer as big as GKR anymore. It's as small as regular gross 16. Does it make sense?
Yeah.
So this is recursion. Yeah.
How does parallel proving work?
So the thing with proving is that you already know the way proofs works is that you generate a trace. So you have a computation and then you just generate a trace. A trace is just like you're writing all the steps in a computation. All the steps, like everything that you saw as you were computing it, you're writing it all down. Then once you're now done with this, you now prove that everything is connected correctly. But the cool thing that you already have is that you know how everything is from beginning to the end. So this means that you can break up that proving step into smaller proving steps, then run them in parallel, and then connect everything back at the top.
The reason why I'm asking is because of the bias to, I don't know if you know about it. So I think two is like trying to enhance parallel proving, whereby you're proving multiple
At once.
transactions at once, not the sequential proving where everything goes.
Exactly.
That's why I asked.
Yeah. And then even Scroll, they had this Seno project where they did something like this too, where you prove in parallel and then you connect it. But the cool thing is that you don't have to be sequential. Like a regular computation, you cannot know what's going to happen in the future until you have done what you need to do in the present, right? That will now tell you what you need to do next. So the computation is like sequential, except for like parts where you can like separate it. But then when you're proving, you already know everything. So you can split it up arbitrarily and then just prove everything. As long as you have a way of connecting it, yeah, you join, you need to join it. So they use lookup arguments to join, mostly. Lookup arguments to join. Lookup. Lookup arguments. This is another really interesting part of ZK. This is another really interesting part of ZK. There's a new paper that came out recently. It's called Twist and Shout. Yeah. I don't know why they did that. So it's called Twist and Shout. It came out recently. What's that? Recursion. So you have two proof systems. You have two proof systems, right? You have one that has a fast prover but large proofs. Alright? Another one that has a slow prover but small proofs. Both of them you are not happy with either, right? You don't want to have the large proofs because we are using an on-chain verifier. And the other one, you don't want to have a slow prover because it's just going to take ages to prove. So now the slowness of the prover is based on like how large the statement is that they want to prove, right? So the larger the statement, the slower the prover. Okay. So the slow provers are not so bad if the statement that they are proving is small. Okay, it's still manageable. But the statement they're proving is large, it's no longer manageable. So what you do is that you use the first proof system, the fast prover, big proof, to prove the very large statement. Okay? but it's going to prove that really fast relative to the other guy. But then the problem is that you're going to get a large proof. But it's not large as long as the statement itself. Okay? It's large relative to what the slow prover will have given you. Let's say the slow prover will have given you something that is just a constant group element. But then this one is going to give you maybe like a vec of some field elements. But that's small relative to the huge statements that I started with. So now you're not in this situation whereby the slow prover is manageable in the sense that it can prove this small-ish statement, even though it will prove it slowly, but the statement is small enough that you can live with that. Okay? So that's basically you use the fast prover to generate a small proof, then use the slow prover to verify and prove at the same time that, and then give you like a really tiny proof. So at the end of the day, the cost of proving is like really small, and then the proof size is also really small. Then you can do this continuously. So even the like GROT16 output, you could wrap it in something else. Obviously, it doesn't make sense again for like GROT16 because it's constant. But usually, what happens is that they use many intermediates. Then GROT16 will not be like the final boss, right? Maybe like the statement that JKR outputs is still too big for that slow GROT16 prover. So instead, you want to reduce it more. So you use another proof system to kind of like reduce it a bit, and then. But at some point, you cannot just do this infinitely. At some point, there's like diminishing returns where you're no longer gaining anything for. This is just proof recursion. It's just like a side. But does it make sense?
Yes.
Alright. Then for Merkle trees, we understand commit, right?
Yes.
How to commit to a vector. Then we know how to prove membership. And we know how to verify the Merkle authentication part. So for Merkle trees, it's just anything for now. We're not talking in terms of polynomials. It's just a vector of items. It's just a right hand. So it doesn't care about what is inside, as long as what is inside is hashable. That's all it cares about. Make sense? Sure? Oh, you're not here. You stepped out. So this is how verify works. Do you understand the proof? This is the proof. You understand this, right? So verify is just like you take the thing you're trying to prove membership of, which is C in this case, right? And then you hash it with the first. So you get C. You understand now?
But okay, the proof is just the statement.
Proof is just the vector of like, and then verify is like. So at the end of the day, you just check whether this is equal to the commitment that was sent to you earlier. If it's equal, then you return true. If it's not equal, then you return false. Make sense? Cool? So the next thing we want to look at is how does FRI ensure that the degree is not more than a certain D. Yes, it's capped. FRI ensure that the degree is capped at a certain yeah, a certain degree D. You said? Yeah. You go back for a second. I need you guys to be awake. Oh. It's about to get real. Okay. So before we go in there, we need to talk about something called error correcting codes. Not in too much detail, just enough. Huh? Yeah, the space is wide. The space is wide. Huh? And it's young. But some things are getting, how do I put, they are getting like deprecated. Yes. So there are some things that people used in the past that they won't use anymore. But then it's still useful for research purposes because of there might be an idea in something that is old that can be useful for something that is. So it's not enough to just like say, oh, I'm like what I'm doing with elliptic curves. It's not enough to just do that. You should not just do that. So if there's a need, I'll go and look at like the details of that. Right now, there's no need. So you still need to look at the broad. But then with time, it gets faster. Like faster to pick up because the ideas are similar, especially if you are trying to understand in depth. Like when you go like 2 layers in depth, the ideas are almost the same everywhere. Like all lookup tables now, they have similar ideas. The proofs, PCS, polynomial constraint schemes, they all have different ideas. You guys still see that quotient thing here again in FRI. There's a multilinear, so FRI is like univariate. There's a multilinear version of FRI, which is called base. Yes. So basefold is a proof system like FRI, but applied to the multilinear case. Then there are other ones too. Yes. Because before they were working with like curves and all those things, so they were all using like univariate polynomials. Like there's a line where all proof systems previously were all univariate polynomials. Then there's just like this point where things just change, and everybody moved towards some check-based proof systems. So that's where multilinear comes in. So anything that is using some check has to use multilinear. So they needed to now start getting the PCS equivalent for this new field.
Now, maybe another type of
Yes. Like
superlinear.
it's possible. Or multivariate, exactly.
Which is not private?
So
Exactly.
Binions now is a proof system for proving binary fields. So you know how you have fields that like BN254, right? Like all the field elements are really huge. And then you now have Goldilocks, where all the field elements are 64 bits. There's now another paradigm of field elements, which is just 1 bit. So like every field element is either 0 or 1. Okay? Which is like very similar to how the computer works.
Yeah.
So before there were like hash functions that they call it ZK friendly, like Poseidon, Ketchup, because of SHA-256, all those ones, they use binary under the hood. And our proof systems previously were not good for those kinds of fields, right? Because of, imagine representing a 0 or a 1 in such a large, like it just doesn't make sense, it's too slow. But then since Binios works natively with binary, all of a sudden those hash functions were now practical. And then the cool thing is that they feel like Binios can be hardware optimized, like really hardware optimized, just because of we have been, the entire computer industry has been working with binary. So they'll just like kind of like move that expertise into this new. So that's Binios, binary fields. Then FRI Binios. So that's like what you're saying. FRI Binios is now, how do we get a PCS that can work with these binary fields? So they just like took FRI. It's like basefold applied to, or FRI applied to binary fields. So they now did FRI Binios. So that was it. So that's FRI Binios.
What do you mean by all field elements are either zero or one? Is it like
Yes. So they have like towers of binary fields. Well,
Because there's something you mentioned, is it Goldilocks or something?
yeah, Goldilocks
Goldilocks.
is a field. The same way you have BLS. Yeah, there's Goldilocks. Then there's Mersenne 31. Mersenne. Mersenne 31. So Goldilocks are like 64 bits. Mersenne 31 are like 31,
Yes,
31,
Venus are binary.
0 there. Just like, but then there's some, don't worry. But you get the idea.
Yeah.
This is just like landscaping. So just be asking if you want to see more about like
Then you want for 256.
commitment scheme. Yeah, KZG for example.
Okay, 256.
256. I don't know if there's a 256, but
Like
I guess.
The Goldilocks is working with like
Yeah.
64 Venus and all that.
I don't know if there's a field that is like. It's just to check. I think there should be. I think SecP. Yeah, sis. Yeah. Yeah, it's an elliptical curve. This is what Bitcoin is based on.
Yeah.
Once quantum comes, bruh.
Just
I laugh. Yeah, you have to do everything. So they have to move the entire crypto. So it's two things, right? Some people don't believe that. Some, no. Some people don't believe that quantum computers will come, right? So that's new information, right? Then they will now update their beliefs based on that. But before that, they didn't know, or some people still right now do not believe that. They know it exists, that like it's possible, quantum computing. But then that humans will be able to engineer a practical quantum computer. Some people don't believe it, and some people say it's still far.
The point is, every computer will come from.
They don't be, no, I don't.
I
It
feel
will
like
get to that point.
No, they are saying that
Like
they
how-
have different advantages.
I feel like the day it will come to life is the day there will be like a major hack. You just see
Practical.
It
Who's
becomes
wallet?
like
You
mainstream.
just say
Wait. You guys can calm down. Quantum computing and classical computing. One is not going to. They are going to work in. They have different. Yes. So that's why I'm like, I'm not sure you should expect that. Oh, all classical computers will just.
But the solution will be inferior.
No, not necessarily. Depends on the use case. They say that quantum computers I've not looked deeply into it, but it's like they are good for searching an exponential space. Yes. Like searching an exponential space. They are really good at doing that. And Bitcoin and all these things, they are based on the hardness of discrete log. And all this like, so it's like they might be able to search for the actual discrete log way faster. Exactly right. All of that. So they are good for those use cases. Well, we'll see.
is it that they can't use it to hack someone's money?
It's a hard problem. Not MP complete. I don't think that's complete. So this is the thing. There's quantum. If you look at the complexity zoo, there are problems that quantum computers can solve, and then there are still like MP that are separated. Yeah. So because what you're driving at is that quantum computers will now be able to solve all MP complete.
Yeah, actually, yes. So, but if the thing is that if every MP problem, every MP problem, if you figure out an algorithm that solves one MP problem, it solves every MP.
Yes, that's why when he said discrete log is MP complete, I was like, are we sure it's MP complete?
Is it MP complete?
They said no one knows, bruh.
No one knows.
The article is wrong.
No, he's actually, that's his own point of view. Actually, he was giving his own point of view.
It's a.
This one is another person POV.
Quantum computer would be like where alien is living there.
Okay, let's continue. Error correcting codes. I don't want to go too deep in this, because we just want to leave. Error correcting codes. Codes. I'll write it. Can you see it? So the idea is this. The idea with error correcting code is that's the original idea when it first came out. They had like this telecom, that's like AT&T, but like MTN, all these things. So they had channels that you can use to send information, right? So you send messages through this channel. So like there's a person here, and then there's another person here, and then you have a channel. Like you can send a word, you can send something in here, it's passing through the channel, and then it goes out to meet the other person. So the problem with this is that this channel is noisy, okay? So meaning that if you pass information through it, noisy, yeah. So noisy, something like that. Yeah. So if you send your message through it, before it gets out on the other end, something might have changed. You get? That's what noisy is. So error would have been introduced somehow. So let's say you wanted to send 111, and then it now goes out as 1.
Said something about echoing, like shout, like echoing. So maybe you are here, outside, another person is outside. Then one person will say a word, the next person will repeat it, the next person will repeat it.
Exactly.
So that, I think
That simulates a noisy channel from the first person to the last person, for example. So by the time it gets to the last person, somebody will have exactly. So so this is the problem that the problem error correcting codes are trying to solve is that if I pass a message, who's playing music? Okay. If I pass a message, I want the other person to receive the message I am sending, basically, regardless of the noise that this affects. So I want that even if errors occurred, I want the other person to be able to correct or reconstruct, to correct it. Does that make sense? Yes, to get the original message back. That's the goal of error correcting codes. Okay? So there are different error correcting codes. The one we're going to be looking at is Reed-Solomon codes. Reed-Solomon codes. This is what FRI is based on. And there are a lot of terms today. I'll just try to give as much info. Brain dump. I give brain dump. So one naive way of doing this, right, is to repeat every bit. Let's say 3 times. Right? That's possible. So this 111, instead of sending 111, I would repeat each bit 3 times. Okay? So A is like 111, then 111, then 111. Does that make sense? Now this noisy channel has a probability of like causing errors. So let's say it only changes a bit, right? If it only changes a bit, let's now assume it's now 111, 101, 111. Okay? Now you can use majority to kind of like determine what has happened. So you look at each chunk and see what's the majority bit here. That's 1, right? What's the majority bit here? What's the majority bit here? So that's how you get the original message back.
What if it is 111 like 4? You have it 4 times.
Or 10.
You could do it 4 times, yes. No, 3 times too. No, this is just I'm just giving you an example of how you can encode a message so that it can be corrected later on. This is a dumb, no. This is a very,
Because there are so many faults I can see. What if the entropy is more?
so you choose the duplication rate. You choose the duplication rate based on the error, how noisy that channel is. So I'm like, this channel only messes up 1 bit. That was like the condition. So you'll have already like measured like, okay, this channel is a very noisy channel. Let's say it messes up 10 bits. Then you know that, oh, I need to add a lot more redundancy. Like each bit will now be like 20 bits. And then 20 and 20. And then I send that information, right? And then just take the majority still. So there's a trade-off here, right? You guys should really see a trade-off. There's a trade-off between the original message length and the code that you have generated. You don't want it to be too, right? How smart the code is dependent on how. So what they're trying to minimize is, I want to still be able to correct errors without duplicating more than I need to duplicate, or without adding more redundancy that I need to add. Does that make sense? So that's what everybody's trying to, different error correcting codes are trying to like solve. That's called the blow up factor. The blow up factor is like, how much should I blow up the entire distance? So this, for the ambitious amongst you, there's this woman, Mary Waters. She has this playlist, algebraic
and welcome to this introduction
coding
to
theory.
algebra.
This goes into error correcting codes, like in detail. So if you really want to like look into this, then you can use this. I'll send the link. You want to get back the exact input. What's correct? So, like, depending on the code. So there's something called a code. The code is like the family, the set of algorithms and everything. So in this case now, so let's define some terminologies. You have a message, right? The message is what you're trying to send. Yes. But then before you can broadcast it, you need to add redundancies, right? You need to add extra duplicated information somehow, so that when an error occurs, you still have enough to be able to recover back the original. So like you're adding more bits of information. of duplicated information. Not duplicated in, let's say, this sense of duplication, but it's just like information is, there's something about, like, you are trying to pass a certain information to someone else. There is the minimum amount of data that you can use to pass that information. But then you can still pass the same information with extra pieces of data. But just that some of that data will now be rendered redundant. So you have a message. There's something called encode. So you encode a message to get something called a code word. Okay? So all the messages will be converted into a code word. In our case, 111 was converted into 111, 111, 111. So that's the message, and that's the code word. Now this code word has properties that allow you to correct if there's an error. Okay? There's a way you can detect whether there's an error, and you can also correct an error that exists. So for example, in this case now, how do we detect if there's an error? If every 3, right? It's now chunk 3, 3, right? If they're not all the same in in every 3 groupings, then we know that something must have happened somewhere, right? We can detect an error. In this case, it's obvious that there must have been an error here. Because our algorithm is that you take whatever bit it is and you duplicate it 3 times. So all 3 groupings must be the same. If they're not the same, then something has happened. So that's error detection. But then this also has error correction. In the sense that you just take the majority. But it's not every time you can do that. Like in this case now, if 111, then 100, let's say it flipped 2 bits. Now, even if we follow the algorithm, we can detect that there's an error. We know something has happened. But if we follow the correction algorithm, we'll have 101, which is not the original message. So this one is not resistant to 2 errors in the same grouping. So your code word will know the limits. So you just have to make sure that your channel does not surpass that limit. Does that make sense? It's information theory. This is literally what made Cloud Channel. This is it, yeah. Coding theory is a branch of information theory. It came out of information theory.
But if it's like this, according to, okay, I don't know if it's related, but you mentioned about this is more than enough, right?
Yeah.
So, like, still on information theory, and like, according to the Pigeonhole principle,
Yeah.
Pigeonhole principle said that if less number of more number of pigeons with less containers,
Yeah.
each hole should have at least 1 pigeon.
Yeah.
So, does that apply to redundancy or that like compression or something?
I guess you're trying to use Pigeonhole.
Redundancy like that? Because we are not following the Pigeonhole principle.
But so different codes, right, have different ways they do that redundancy in introduction.
Okay.
So this is just one way, right?
Okay.
Where I just duplicated. Now with the Pigeonhole, I'm sure you should be able to come up with an encoding scheme using Pigeonhole theorem, but it's not like what we used there. But I'm sure you should be able to. So are we good now? So we have a message, right? And we have a way to encode the message into a code word. Now this code word has something called distance. So it's like how close is one code word to another code word. Okay? That's what we're talking about. Yes. So yes. So if you look at the space of all possible code words, there's a distance. So let's say you have a code word here. You have another code word here. You have another code word here. Code word. You have another code word here. So your encoding has put like some structure to how the code words are close or far from one another. So then you now have a radius. Let's call this. I told you.
You are already doing math.
I told you. You guys don't know what you're sleeping on. They don't know what you're sleeping on. So this is.
This is open board.
Yeah, exactly. There's something called humming balls.
It's called what?
Humming balls. This is what they are talking about. This is open balls. Oh, humming. Yeah. So I don't know. I won't say one is strictly better than the other. They all have trade-offs. There's always trade-offs. So there are some that have like faster encoding. You get? That's like to take a message to a code word is really fast. There are code words that have that. Then there are code words that have best distance to message ratio. That's that. Remember what we're talking about? That you are trying to make sure that you add enough redundancy without, let's say, blowing it up unnecessarily. So there are some code words there are some code systems that they are optimal. So Reed Solomon is optimal when it comes to that. They call it like MDS codes, maximum distance separable. So, I'm not done yet. I want to just say something. There are different levels of FRI. Okay? There are different levels of FRI. There's a way you understand FRI. You will be able to implement it, but you will not know. You will know what you're implementing. There are levels. So you know just enough to be able to implement. So there's a way you understand this, like you don't even need to look into code words at all, right? So I'll send you guys a video, Stack 101, where they explain FRI. They won't show you the code word side of things, okay? Then there's another level that you go in. So it's just like you're just going deeper and deeper. Depends on what your goal is. Depends on what your goal is. But to implement, depends on where you want to be. You want to run, are you? Separable. Which one? MDS. MDS or the circle. Yeah, so these are the code words. And then this is I think this is the minimum distance between two code words, two valid code words. So there's something interesting here, right? Like if one of the code words, right, there's an error, just like some bits were flipped, as long as that bit flipping is still within can you see this? So we have the valid code word here. This is the valid code word. Then we send this to a channel. Then when we send it to the channel, this is what came out at the other end. Right? The red. So the white is valid. That's the message we wanted to send initially. So we encoded our message and we got that code word. I then want to send that over to the other person. But then the channel is noisy. So he changed some things. When he changed it, we now ended up with this red.
The red no, as far as the red is within
Yes,
that neighborhood.
exactly. Not we don't call it neighborhood, yeah. But yeah, exactly. So as long as the red is within this, we can take it back uniquely to the center.
So in math, we will call it interior point.
Interior point.
Yes.
I don't know what interior point is. Well, what is interior point? The code word? The white?
Like the red.
Oh, the red.
Yes, it's called
Oh, it's
interior point. It's still found in the bulb.
Is this under topology?
Yes. This topology.
You guys should learn your topology well.
This topology is called matrix-based topology.
You guys should learn your topology well.
Level to them.
Listen to them.
So what is
Because it might be useful for research.
They know the white.
Yeah.
The white.
So different messages will give you different code words.
No, it's not completely. Any point.
So you can, but in this space, it's just space of all possible code words. So it's like, if your message is of length 2, right? So you can send 00, 01, 10, 11. This is what you want to send. These are the possible messages you can send. So rather than, so these are the possible messages you can send. So instead, you now have this encoding. So let's say the encoding is still, let's say the encoding is still that like duplicating 3 times, right? So this will be 0, 0, 0, 0, 0, 0, right? Then this will be 0, 0, 0, 1, 1, 1, 1, 1, 1. But I'm filling each bit 3 times. No, each bit 3 times. It depends, no. That one too is another code scheme. Right? You just have like, they all have their encoding formulas. Does that make sense? So now these are going to serve as the valid code words. The white dots. Okay? So it's like, this one can be 0, 0, 0, 0, 0, 0. Then this one is 0, 0, 0, 1, 1, 1. Then this one is 1, 1, 1, 1, 1, 1. And then this other one is 1, 1, 1, 0, 0, 0. Okay? So now, we're saying that, okay, you intended to send 1, 0. But then something happened, right? But instead, you now got 1, 1, 1, 0, 1, 0. Right? It is no longer what's in the middle. A bit has been flipped. But it's like, it's still discernible that this must have come from this guy in the middle. You get? So we have not like applied, not enough errors has occurred that we cannot discern it anymore. You get? So now we can go back. So there's something called a decoding algorithm. So decoding, we have encode, we also have decode. So decode will take a code word, right? And then to give you the closest message. You have closeness in this one. You have boundary.
So far that it's still
Within the boundary.
within the white whatever.
Yes.
So that is boundary.
But then if it's now like on the white thing itself, then you can detect that there's an error, but you can no longer bring it back. Do you guys have that? Yes. So let's say it was here, right? Now it is equally close to the left one and equally close to the right one. So, but you know that there's something wrong, but you cannot tell. You cannot correct anymore.
But that's if it's dead at the center of like bound.
Yes. But then it cannot be problematic if it came from here and then entered here, and you'll be deceived to think that it's the other one. So that's why you need to know the error probability of your channel and make sure that you're not using a channel that your code cannot handle.
So basically use your wider.
Yes, exactly. So if your error is larger, then use a wider radius, which is like something with more distance. Does it make sense?
Yeah.
A code word is the result of encoding a message. That's like after you have added redundancy to the message, that final thing you get, that's called a code word. So all the whites are code words. So giving your message space, like all the possible messages you can send to somebody, these are the equivalent code words for those messages. Now you have added redundancy, which is what is giving you that like radius, the distance. We call it distance, yeah. And then yeah, so this is now it. So as long as if let's say this was what you intended to send. Let's say this is what you intended to send. As long as the error is still within the boundary, you can now uniquely decode back to where it came from. In this other case, you cannot do unique decoding anymore, but you can do something called list decoding. That's
within the boundary, but not including the boundary.
No, not including the boundary. You have to be within it. But if you are on the boundary, it's not like you are sharing a boundary with another
Some other
code word. So you cannot like decode uniquely anymore, but you can say I am one of these two messages. You get? I am either this or I am this. So that's list decoding. Okay?
You say something. If you want to view it, it's math. That means the board is open.
What does that mean?
Because according to what you said now,
Yeah.
if the message falls on the boundary,
Like this one now, right?
yes,
Uh-huh.
you can't really detect it.
You can't uniquely decode it.
Yes,
it's not within.
it's not within
Anyone,
so
yeah.
If it's close, you can detect it.
If it's close to one. Yeah,
So
if you
like if the board is closed,
Oh really?
yes.
Yeah, but if it's open,
If it's open, you can't.
How would you decode it? How will you choose which one?
Look, for example now, what we are configuring now is open board.
Okay.
So I'm just saying that for us to uniquely, I only know math definition. An open board. I don't want to say math board. When we have a distance, let me just try and when we have a distance,
Mm-hmm.
I get it between x and y, it must be less than 3. So that is just what my open board is. In layman. No, like I have a distance between x and y. Like I have a set. The set, then I pick 2 points on that set. It must be less than 3.
Is it for every x and y?
Yeah.
That's for any x and for any
Let
y.
me confirm that.
So it's just like, for instance, me now, I draw a radius around myself.
Yeah.
This guy is, as far as I can pick 2 points that fall within the radius, I'm a ball. No, let's not
Wait, is
say
it just
ball.
2?
So what's that?
Like any point,
Any
like
point
if you pick
for all
any
x and
point,
y.
then you can just say x for all x or no.
That is not
As long as
from
you
the
fall
boundary.
within this,
So it's like
that is
Like
a
the intercept.
So what's the
Like intersection.
Close, but for example, the open board is dotted, like it's not circle like this. It's just like something
yes,
like
you're there.
dotted.
So what is
The
The
boundaries
closed
are
ball
not
is what you
included.
draw.
okay,
The boundaries are not included in the set.
for an open board. Okay, but for the closed board, the boundaries are included.
You guys should look into that algebraic. Well, after your exams, look into the algebraic. Then try and draw parallels Do you get? That's like how it's related to topology. Then the choices that they made. That's like how is it different from this? Then I'll see can what happens if I still use this thing that they didn't use that is in topology, and see if what the implications of that are. That's how you come up with new news exactly.
So, I have layman definition. So it means that open ball consists of all points whose distance from x naught, like a point in the set. If I pick 2 points inside the set, it will be less than the radius, excluding the boundaries.
Any 2 points.
Yes, within the set, excluding the boundaries. So, closed ball is the reverse. It includes the boundary. Closed ball still talk about I pick 2 points. It will still be less than the boundary. It will still be less than the radius, but it includes on the boundary.
From this now,
Yes.
but since we're talking about it, even if we're talking about, from what I'm seeing now, even if we're talking about the close and open, then from what he's saying here is that if it falls on the boundary, where both of them where they touch, it's almost the same as okay, so it's like the like it's open. So this side and this side come together. So that is open. So it's like an intersection. So it's intersecting here, and down one is still intersecting.
So what we are trying to say
So
is
at that point, you're saying that if it's at the intersection, at the boundary, the boundary is still the intersection. So we're now saying it's whether here or here.
I get what he's trying to say. So what I'm saying that it's possible to do that because the possibility is because it's open. For example, now if we are considering a closed ball, we know definitely because the closed ball contains the boundary point and our point is inside the boundary. Are you getting me? It's just like I don't know how to.
If it's close, that means they're not touching. That means they're just
Two closed balls can intersect. We have what we have separate sets, we have connected sets. Connected sets. So when we talk about two sets are said to be connected if I can find the intersection between the boundaries of the distance.
So we have this, where would this go to?
Please check. I want to confirm my.
Where would this go to?
Eh?
Where would this point go to?
I think this is connected sets.
And it's too
I
close
may not be
now.
able to. This concept is new. I may not be able to break it down up to what we are doing. I'm coming
Yet.
from math.
Yet.
So yet,
Put in the
like,
work.
I'm just inferring that
Alright.
these things are familiar.
So let's continue. Let's continue. So now let me define Reed Solomon. Okay? Reed Solomon code. Just a basic definition. So you have your message. Usually your message is let's just say a vector of field elements, for example, right? So you have A, B, C, D. So this is what Reed Solomon does. You know, the goal of you have your message and you want to extend your message into a code word, right? By adding redundancy. But the way it does this is that it will interpolate this to get a polynomial. Then it will now evaluate this polynomial at more points. So easy. So let's say the block factor is equal to 2. It means that our code word is twice the size of our message. That's what block factor equals to means. If block factor is equal to 3, then our code word will be 3 times the size of our message. So once you know the block factor, you know how many more points you need to add to this. You know, our goal is supposed to be 8 now, right? Now we need to evaluate it as 4 more points. This is your message. We want to encode it using read Solomon, which means we want to add more redundancy to it. So what we do is we take this message, we interpolate it. Let's say you use something like Lagrange, but in production they use FFTs.
This will be very
Yes. Then you get a univariate polynomial
So which one do you use for the interpolation?
and the evaluation. Right? So this is like the XY parent. Interpolate it to get a polynomial f of x. Then this f of x, you just evaluate it at 0 to 8.
0 to 8.
7, sorry. Like 8 values, right? So this will still give you A, right? This will still give you B, C, D. Then this will now be like just like E, F.
Why is it?
What?
Because of my blow factor. I chose a blow factor of 2, which means that my code word is twice the size
Okay.
of my.
Alright.
But is it possible that if this is not evaluation that you want to
Yes. So in like when you're doing with Solomon using FFTs, right? Which is how you're supposed to do it. Like you should not be doing it with regular Lagrange interpolation. The interpolating set will not be 0, 1, 2, 3. The interpolating set will be the roots of unity. Okay? We'll go into details as to what that means. Roots. It's the roots of unity. It's not going to be 0, 1, 2, 3. It's going to be the powers of the roots of unity. Okay? Root of unity is basically just like n root of 1. We'll go into detail as to what root of unity is, but for now, just take it as a black box. Just understand with Solomon itself first, right? You take a message, you interpolate the message to get a polynomial, and then you evaluate the polynomial at more points. That's how you add redundancy, right? So then this is now a new code word of a longer length. But the two of them share the same degree. Does that make sense? Like if this is degree D, then this one is also makes sense, right? Because you remember the 2x plus 1. Yeah, this one. Technically, this is representable with just 2 points, right? You could do like 0 and like 1 and 3, right? But then evaluating at more points doesn't change anything about the degree. It just extends the size of the code word or the amount of redundancy that you are adding to the code word. Does it make sense?
So, sorry. So for that, so I can also do that. So you say normally for that FLX, you're not supposed to be doing that. You're supposed to be doing that.
You can use Lagrange, but it's going to be so slow.
It's not so slow.
To be really slow.
Okay, to be really slow, so you have to use FLX.
Very slow. So we'll still look into FFTs, not today though, probably tomorrow. And then we'll look into roots of unity also.
And what it does is that you don't use the block factor to be able to and
Yeah,
that extra points.
redundancy.
Okay, so that is when the FFT will factor for the ability.
So FFT is what you use to convert from this to FFT. Yes. Fast Fourier transform. I think Ekarika and Uche have implemented FFTs already. I just chose it. So I'll show you. No, there's a. So depending on the how noisy the channel is, the block factor will determine how much error you can handle.
How do you know how noisy the channel?
So in our case now, we don't really care about. We'll also figure out how much error you can handle based on your given blob factor. Okay.
When you say how much error can handle,
if something
how
happens.
far off you can go, like you
Yes.
travel back to
Yes. So it's like, let's say you're here. Let's say this, if this was the size, and then this other one had this, right? This one is more resistant to changes, right? Let's say like 1 unit of error will move it here, then another one will move it here, then another one will move it here, another one will move it here. So as long as it's still within, you can still always go back, right? But then in this case now, once you have done like 2, you're already at the boundary, right? So if you do 3, then you can't do anything again. So this length of that, the blow up factor is directly correlated with like the radius. You get. So if you do a blow up factor of 10, you're going to be creating like this really huge radius. But then the problem now is that your code word is now like really, really large, right? You went from 4 to 40, which is going to affect the prover's time, because the prover is supposed to do a Meko commitment to that code word, which is like a lot more hashing. Someone wanted to ask the question. I said someone wanted. Do you want to ask the question? And evaluating at more points based on the blow up. So now, okay. Yeah, so I wanted to give like the distance, okay? So the distance is how, like there's something called the minimum distance. Minimum distance is how what's the best way to explain this? Like how much will I have to change in one code word to make it look like another code word? It's kind of like, I'm coming. Let's just think about it from the first principles. I'm missing something. So we started with 4 values, right? Which is a degree 3. This is degree 3, right? Right? Most likely, because 4 values, t plus 1. Then we did a blow up to 8 values. Which is supposed to still be what? Right? Nothing changed. Now, if we had a different message entirely, let's say M, N, O, P, right? It's a different message now. This message will also go up to another degree 3. Yeah, but 8 values now. M, N, O, P. Right? Now, what we care about is like, what is the distance between these 2 code words?
You need the distance of the radius of 2.
That's like distance. That we want to know, like, is it like how much can it sustain? That is still like decodable. I don't know if that makes sense. But let's first see the relationship between the 2. If we have 2 polynomials of degree D, how many values can they intersect at?
The
2 different polynomials
with the same degree.
with the same degree.
That means
It was Zippo lemma. They can only intersect at at most D points, right? Right? So this means that regardless of how much you blow it up, that D will still remain. Like 2 will only mistakenly coincide at D points, while the remaining would be different, right? So let's just say like this is what is the same. It means that the rest of them are different. So that means it's still. So I'm trying to see like what the error has to be before it is not decodable again. I think you have to do more than.
We said it already. Look at. You said what we are our blow factor. That is depending on the blow factor.
Yeah, blow factor will play a role.
Yeah, it will play a role. So depending on the blow factor you're going to use, you will now determine the radius, the distance of the error, whatever. So since the blow factor is not constant, so it's I think it's.
In this case, it's 2. I'm coming. In this case, it's 2.
It's 2.
Yes.
Okay, we are specific now.
Yeah, in this case, we're specific that it's 2. What needs to happen to this before we would not be able to decode it again?
I think it will just be too hard.
What is the maximum? So, wisdom, let me get something. So, let's say you have that center point, which is the message. You create let's just say a neighborhood of a kind of entropy, so that the messages that look like a message will have some discussion in some point. So that's like the neighborhood around the message. So now the question now is that what kind of message are we going to get that we say, okay, cannot go back,
Yes.
cannot be.
Yeah.
That's too
Is that the question?
Yeah, that's what outside. I'm trying to say like how many things do I need to change to push it out?
That is how much entropy we need to create in that message for it cannot go back to the original.
Like if you change 1, I think you can still go back, right? Let's say I change H to M. I should still be able to go back because it's still unique. Like I still have 7 things that are related to the center point. So I'm trying to say like what's the point where I change, and then I'm not going to an indistinguishable point. That was looking like once I start eating into the degree, that's that 3. That's like it might now get yes. Yeah. So what am I saying now is that if I change this, it's still fine, right? Because there's still some uniqueness, right? If I change this, it's still fine. If I change this, it's still no. I think once I change, I think at this point it's still fine. But then at this point, it seems like it's no longer fine because of it's possible that there could be another code word that shares those 3 values exactly. So there's now like ambiguity. But I'm not sure about this. But I think
Boils down to that shows
yeah, it's really not sure the ambiguity comes when you have changed everything other than D. In that case now there could be something else based on Schwarzschild that could have the same D point.
yeah.
And then at that point it's
I know we need to check. I don't remember that they were like, we need to check plus 1.
so D plus 1. So if it's like D plus 1, I think we're fine, right? Because there's still 1 extra. That's the D plus 1 that makes it unique somehow. But this is not important now. No, I'll go back home and I'll check this in more detail. Then I'll come tomorrow. But what really matters is that you can take the message, interpolate it, and evaluate it at more points to convert a message to a code word using Reed Solomon. Make sense? So this now, you know the first part of FRI. So this is what FRI does. You're trying to commit to a polynomial.
So before you go, so you say we get the message.
Yes.
Do we blow it up first before we interpolate?
No, you interpolate to blow up. That's how you blow up.
So we interpolate it to get a polynomial.
Then you now evaluate that polynomial at blow up number of points.
Or we still, but then the way I'm seeing this now, we're using A, B, C, A, and then A, B, C is still part of the.
It's an extension. So it's like A is like the evaluation of that polynomial at 0. Then B is the evaluation of the polynomial at 1.
We just added extra.
We added extra. But you could also have like gone to another domain. Rather than starting from 0, 1, 2, 3 again, you could have gone to somewhere else. But usually it's just like a repetition. You just extend it. Make sense? Usually it's not actually. Right? You go to another domain. But it's fine. So
So the ones you're interpreting are the
for FFTs, yes, which is how you would actually do it. But for now, black box, just take a message, interpolate it, evaluate it at more points. That's how you encode. Make sense? So now for FRI, the beginning of FRI, the goal is to commit to a polynomial, right? You have a polynomial. That polynomial can be represented in evaluation form. Cool?
Yeah.
So that's like wanted to commit to f of x. 2x plus 1. That one we can relate to with what? 0 will be 1, right? And 2 will be 3. Yeah. So this is the evaluation at 0 and evaluation at 1. This is our message. Our message is the polynomial we want to commit to in evaluation form. Okay? Then what we do is that we now do the Reed Solomon encoding of this message with a certain blow-up factor. So let's say the blow-up factor was yeah, it's at 2, that's what? Say 5, right? And 7. So then this is now our code word. This is what we now do the MECO commitment to. Okay? So you interpolate the polynomial, you blow it up, and then you commit to this polynomial using the MECO tree. So that means you're going to merge this with this, right? Then you merge this with this. This root hash is your commitment. Okay? But then, you know, we had a problem, right? We need to ensure that the degree is bounded. We have not yet solved that problem. And we will not be solving that problem today. We'll solve that problem tomorrow. I have to go back. We're working on something right now. So I'll just sketch it briefly. What happens, okay? So you take your code word, the initial code word, you commit to it to get a MECO root hash, right? Now this code word, you are saying that it should be degree D. Let's say the degree you're saying it should be degree degree 10, for example, right? You don't want it to be more than degree 10. So this is supposed to be bounded by degree 10. So what you do is that there's something in FRI called a folding. Okay? So you fold this code word into a code word of a smaller length, half the length. So you're going to get a new vector that is half the length. But now this vector has degree. It also halves. Okay? Then you fold it again. What would this be? Wait, let me use a power of 2 just to make it easier. Right?
Is it just to make it easier? Well, is it possible not to give a power of 2?
Yes, possible. You just put the higher bound. Just make sure that you're not making the mistake of thinking the degree is something that go to the max, like seal the degree to be 3. Yeah. So, and then we now go down to what? But now, this one is so small that I can check whether the degree is 1 or not. Do you get? Like I can just the way to check whether a vector has a certain degree. Like if I wanted to do this one, right? What would I do? I will interpolate it and say the highest power of x. That's how I'll know whether it's really less than degree 8 or not. Okay? But the idea is that top one is too big for you to ask the verifier to interpolate the entire thing.
Sorry, this Merkle root now, that's the output of that's the bonus vector.
So you're going to send multiple Merkle roots for each of these vectors.
I'm saying like that first one. Where are you getting that from? Is that the commitment?
Is the Merkle commitment to the first vector. But you're also going to do a Merkle commitment to the next vector and a Merkle commitment to this one also. So the FRI commitment is not just one Merkle commitment. It's a bunch of Merkle commitments.
So what I'm going to do is I'm trying to see the situation behind this whole thing. So this Merkle root it's like an effect of points, right?
The Merkle root is the Merkle commitment to a vec of points. It's like you had this vec of points, right? And then you committed to it to get a Merkle root hash.
Okay, so what is that Merkle root? What is it?
It's a hash.
It's a hash. That is just like a very big number.
It's just a 32-bit number, 32-byte number.
But then you're presenting it as an array.
No, I'm saying you give out the Merkle root of this array. So you,
Okay, the array is
leaf.
the array is the leaf.
So you Merkle commit, Merkle commit, Merkle commit, Merkle commit.
I can't get in the intermediate.
That's the folding. That's what we'll talk about tomorrow.
So why?
Fold the initial vector.
Into half, but you preserve the degree.
So the input to for this one that we did now,
Yeah.
the input to it was 1357.
Yeah. So you have like let's say 1, 3, 5, 7. Then you commit to this, right? To get hash 1.
So but then the purpose of the fold is we're trying to
Reduce the degree.
reduce the degree.
Yes.
But don't we know the degree of this polynomial?
Yes. But the verifier cannot check that by himself. Because of the way to check the degree is to interpolate, right? And then check the highest power of x. Does that make sense?
That's because it's a univariate.
For yes, and also the first one will be really, really large. Right? Like this first thing, in production systems you're thinking about like 2 to the 20. Let's say like that might be the number of elements. So the degree is maybe like 2 to the 20, let's say minus 1. Right? That's a lot of points. So for the verifier to verify that the degree is within that bound, you don't want the verifier to now start doing like interpolation just to check what the highest power of x is. So what you're trying to do, you're trying to make the problem manageable for the verifier. So you fold to now have a degree that is half that size, right? So let's say you started with a degree 8 polynomial. Let's assume degree 8 is too large. So you fold to get degree 4. Then you fold to get degree 2. And then you fold to get degree 1. So degree 1 is just like 2 points, right? So now the verifier does not even need to like interpolate. It just looks at the distance and says, okay, are these just 2 values in this last vector? If they're just 2 values in the last vector, then it knows that, okay, this is a degree 1 polynomial. So what it now does is that the last thing that it needs to do is that it needs to ensure that you folded each correctly. Okay? So it's like you need to prove you folded, and you need to prove that the last thing is indeed bounded by degree 1. So if the last thing is bounded by degree 1, and you folded correctly, then that instantly means that the top thing is bounded by degree 8. Like, it's an implication. Do you get? Like, you prove you folded correctly. If the verifier accepts that you folded correctly, and it sees that the last thing is degree 1, then the only way you could have gotten to this situation is if the top thing was degree less than 8. So that's how the proof works. You fold to get something manageable, then the verifier would now check that small thing himself, and then check that you did all the folding steps correctly. So if you did everything correctly, then that means the top thing must have been what you claimed it was. So now if you lied, and then you now said that, oh, this thing was degree 8, whereas it is degree 16, right? The verifier knows it's supposed to be degree 8. So the verifier will know that I'm supposed to stop after 1 fold, 2 folds, 3 folds, right? The verifier knows it's supposed to stop after 3 folds. So when you do this is the first fold, you're going to get what? 8, right? You do the second fold, you're going to get 4, right? And then you do the last fold according to the verifier, and you're going to get 2. But now the verifier is going to say, okay, give me the last thing in the open, not the Merkle commitment. So you give it the last thing, then it checks, is this a degree 1 polynomial? In this case, it's not going to be a degree 1 polynomial. So that's how the verifier will know that you lied about the top guy. Does that make sense?
What if the program
Lies.
degree 8, but the values in it is not actually the right values, and probably one of them has been changed?
What do you mean, not the right values?
Like, say, is providing the array of 8 elements, but probably maybe it's supposed to be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. But instead of 1, 2, 3, 4, 5, 6, 7, 8, it is like 1, 2, 3, 4, 5, 6, 9, 8. Just to give that output. How will you be able to detect that? Because to still come down to degree 1.
So, what you're saying now is like, remember there's the message and there's the code word.
Yeah, the message, like you're stamped with the message.
You're stamped with the message. Then the proof system itself would detect that. So like whatever it is, let's say you're using GKR, then you are it's basically like you're tampering with the input. So then the proof system will be able to detect that, oh, something has gone wrong. But then if you left the message, but then you tampered with the code word generation. So let's say you've generated the correct code word, but then you just changed something. What's going to happen is that that new code word is no longer going to be a code word for like that message size. It's going to be for like a different message entirely. So it's like this thing is working in tandem with the proof system. So the PCS is just like making it succinct. But the proof system is like, regardless of whether it's succinct or not, I can still do my job, you get. But the PCS is just making the entire thing succinct. Does it make sense?
How is each method generated from each code? Is it the same method?
So you know how to get like a macro from a vector. Yeah. So you just the same thing. After you fold, you get a smaller vector. Then you just get a new macro from that. You get a smaller one, you get a new macro from that. Make sense? So tomorrow we're going to look at how to fold. Right? We're going to look at how to fold into smaller. So you already know how to do like the macro. I already know how to do the Reed Solomon expansion. So we'll look at how to fold.
Can you go through this Reed Solomon just one more time?
Wait, sorry. Yeah?
Joseph, we already know, like, we already edged how to, like, because I know this, you already know, like, that's implement it. So that you know, we've already edged.
We have edged out to, okay. You gotta spend some time. So, okay.
Yeah.
Yeah, so you have your polynomial
Okay.
that you're trying to commit to using FRI. This polynomial is supposed to be less than degree 8, for example, right? So you need something that can both check that the degree is correct and also commit to the values of the polynomial. So what you're going to do is that you're going to convert this polynomial into evaluation form, right? And then you now use Reed Solomon to blow it up into something much larger based on the blow up factor. Then you now make a commit to this, right, to get a root hash. That's your first one, H1. Then you fold, which we'll do tomorrow. So you get a new vector of half the size, but also of half the degree. So if this was supposed to be bounded by degree 8, this one is going to be bounded by degree 4. Then it's kind
another hash for that.
yes.
Okay.
So you now get a new hash, which will be H2. Then you reduce this also to degree 2. And then you get another hash, which will be H3. And then let's say you do the final one, which is degree 1, which is going to be like 2 values. And then, but this one now, you don't need to send the hash anymore. It's small enough that you can just send the 2 values themselves. So the verifier would now like check that these 2 values are indeed a degree 1 polynomial, and then now verify that you did all the folding steps correctly.
From the root
Yes. So if you did all of it correctly, then you can now be convinced that that original one was bounded by degree 8. Then we'll now show you how to do the
So
evaluation.
what we are folding is the root hash.
No, you're not folding the root hash. You are folding the vector,
The blown out
yes, but you are sending the root hash for each
of each
fold.
of them.
Yes. The reason is so that because the verifier is going to ask you, going to query to check that the folding was done correctly. It's going to query from the top all the way down.
So that
But it doesn't
means-
want you to be able to change the vectors after. So that's why it needs your commitment.
Okay, so that
Sorry.
means when you blow up the polynomial,
Yeah.
you commit
Yes.
to it,
Yeah.
get your root hash,
Yeah.
then you fold it,
Yes.
commit to it,
Yeah.
fold,
Yeah.
commit, fold,
Yeah.
commit, you get to the last
Yeah.
one.
So I think it just
Oh, you
he
reiterated?
kind of answered what I wanted,
Okay.
what I wanted to ask. Like for that degree 8 now, we're
Yeah.
going to get like 7 hashes, but we are only concerned about the root hash.
It's not 7 though.
Like
When you fold, it's now 4.
4 then 2 1. Okay, when you hash that 8 to 4, that is the 4 you are talking about. Like I was talking, like when you say the make roots now,
Yeah.
I was thinking like those eight points now.
Yeah.
We fold 2 2 2.
And yeah, but
2 2 2.
okay, let me so see now, right? Let's say this is the 8 I have. I have A, B, C, D, E, F, G, H, right?
Yeah.
So what we'll do is that we'll pair, and then we'll pair, and then we'll pair.
Yeah, this is what I was asking.
So we're going to get just one root
What
hash.
make roots?
So that's all we are sending. Then it's now become 4, right? Just 1. So this is what we're just doing until we have just like 2. And then we just send this one directly.
Just say that.
Yeah, just send that to that. Yeah.
I thought you said we are going to check if it's degree 1 or something.
Yeah, so that's why you're sending it. So that you can interpolate. But it doesn't even need to interpolate, right? Degree 1 is just like, it should be less than. As long as it's not higher than degree 1, then we're fine. So as long as you send 2 things, we're fine. Yeah.
Remember the first Matthew tree example you gave?
Yeah.
That A, B to H. Like,
Yeah.
They explain how to prove and verify.
Yeah.
Just if we want to do this now, using it for this, that new one you just gave, which of them are we going to use?
Which of what?
That written folding thing that we're folding different,
Yeah.
like from 8.
We started with 8 values, then
you
we got 4
a root
values.
hash for that one.
Yeah, we got a root hash
Then
now. That will be
now
this.
became 4 again.
Then we came 4
So
values.
which one are we going to use, like verify like this? Is it that first one?
So during the query phase, so FRI has a query phase. That's where you check for that the folding was done correctly. You are going to create a proof for each of the Meku trees. Yes. So you have a Meku authentication part for this one. Then for the 4 one, you have Meku authentication part. So that'll be for this one. Yeah, one member of this. Yes. And then the other one will have just one member also. So it's just going all the way down. Yeah. So the proof, the result, the answer to a query is just Meku authentication parts for all the Meku trees that have been committed to. And then you do a lot of queries. Cool? So let's stop here. Then continue tomorrow. Please come early tomorrow. See, okay. we'll start locking the door. Once it is 10, I'll lock the door.
Yeah.
Then whoever is here, we'll work with whoever is here. The rest will just watch videos.
So what's the new class starting? It's still 9:30.
It's 9:30. Today, because they were having a program, or they were talking to the people that got evicted.